Hello everyone, welcome back to Math with Allison. Today we're working in our AP Calculus series. So we're going to be doing an AP Calculus A/B test. This is from 2023 and we're going to be doing the non-calculated portion. So let's go ahead and dive into it. You have 1 hour to do this. This is giving me like PTSD. You have about 15 minutes per problem, so that's a good way to time yourself out. So let's go ahead and go into number 3 here. A bottle of milk is taken out of a refrigerator and placed in a pan of hot water to be warmed. The increasing function m models the temperature of the milk at time t, where m of t is measured in degrees Celsius, and t is the number of minutes since the bottle was placed in the pan. M satisfies the differential equation dm over dt, so the rate of change of the milk in terms of time, it's going to be equal to 1/4 times 40 minus m. At t equals 0, the temperature of the milk is 5 degrees Celsius. It can be shown that m of t is less than 40 for all values of t. So let's go ahead and do part A. We have a slope field here for the differential equation. We're going to sketch the solution curve through the point 0.5. So here's the point 0.5, and you can see how the slope is starting. So what you want to do is just follow all these little tiny slopes. You don't want to hit them all. I know that's not a good thing to do. So start off with the first slope, and then you kind of just follow the way that the slope is going. And then it goes something like that. There's going to be like multiple ways to do it. Like somebody might go more this way at first and then even out, but that is the general idea of the way it's going. So that right there is our slope field, and this is only worth 1 point. So for part B, I copy and pasted these all down here. I'm doing this a little different, so you're gonna have to tell me in the comments if you guys like it or not. Instead of me writing it all out, I already have it written out, and I'm just gonna reveal it as we go. So we're going to use the tangent line of the graph of m at t equals 0 to approximate the value at 2 minutes. So we want to find the temperature of the milk at 2 minutes. So let's go ahead and talk about this. We're going to use the equation of a line. So here we have the equation of a line. Normally the equation of a line is written out as y minus y1 is equal to mx minus x1. But I changed it because we're working with m, the milk temperature, as our y and t as our time. So I just changed those two. So we're already given some pieces of information, right? We're already given the first point, and that point is 0,5. So we know m is equal to 5, the temperature of the milk, when t is equal to 0 minutes. So the remaining part in this equation, because we have m1 and t1, is we need to find the slope lowercase m. So we need to go ahead and find the slope at t is equal to 0. So in order to do that, we're going to use the derivative, and we're going to plug in t equal to 0. So at t equals 0, we have m is equal to 5. So I just replace that in our equation. So we get 40 minus 5 is equal to 35 divided by 4. So that right there is going to be our slope. So let's go ahead and plug that in. We have m minus 5 is equal to 35 divided by 4 times t minus 0. So here we can go ahead and simplify. We can add that 5 over, and here we get the equation of our tangent line. So remember, we're trying to approximate it at t is equal to 2. So let's go ahead and plug that in. We can cancel out this 4 and 2. That's just going to leave a 2 in the denominator, right? So we get 35 divided by 2, and then I change 5 to be as 10 plus 2, so we can add those together. We get 45 divided by 2, which can be rewritten as 22.5 degrees Celsius. You can leave it as 45 divided by 2. That's totally fine. So there are 2 points awarded in the problem. The first one is going to be just plugging in and finding the actual slope. So that's going to be the first point. You need to show what you're doing, so you can't just write 35 divided by 4. You need to show the work prior to it. This is super common notation. If you haven't seen it before, that is going to be the derivative evaluated. The line means evaluated at t equals 0. So if you haven't seen it before, that's all it means. It's very common in the rubric of the AP exam, so I suggest using it and learning it if you don't know it right now. But the second point is awarded just right here. You actually find the correct one. Again, you need to show the work to get there, so you need to show plugging it in, evaluating it, and all that stuff. For part C, we want to write an expression for the second derivative, and we're going to use that to see if our approximation from the previous part is an overestimation or underestimation. So first, we're going to go ahead and just take our normal dm dt. What I did though was I distributed that 1/4. So I got 1/4 times 40 is equal to 10 minus 1/4 m. And what we're going to do is we're going to take the derivative of both sides in terms of t. So on this left side, that's where we get the second derivative, right? And on the right side, when we take the derivative of 10, derivative of a constant is just 0, and we get minus 1/4 the derivative of m in terms of t, right? That negative 1/4 is a scalar multiple, so it just hangs out. So we know what dm dt is equal to, right? We can see that dm dt is equal to this whole thing. So we actually need to plug that back in. When I plug it in, we can multiply that negative 1/4 times 1/4, and we get negative 1/16 40 minus m. Now remember what we're doing. We're seeing if this is an over or underestimation. And what we did was we plugged in t equals 0. So what we want to do is see the concavity at t equals 0, see if it's concave up or down. So let's go ahead and check that out. First, what I'm going to do is I'm going to take my second derivative and I'm going to evaluate it at t equals 0. So when I plug in t equals 0, that's when the temperature is equal to 5. So I can replace m with 5, and we end up getting 40 minus 5 is 35. So negative 35 divided by 40. So notice that this is less than 0. It's negative, right? And when it is negative, that means it's going to be concave down. So why does that mean it's an over approximation? Let's go ahead and draw it out. If I have a function that's concave down, and let's say this is the point that we found the tangent line, if we use this as an approximation, it's always going to be an over approximation. It's going to be above our actual function. It's going to be the same thing on the other side. If this is the point, we find the tangent line, and now we're using this to approx values, it's always going to be above the actual values. Now, if it was concave up, you would see that it's the opposite. Here's a function that's concave up. Let's say this is where we find our tangent line, and we want to use that to approximate values. So we can see that our values are always going to be below the actual values, and that's going to be the case on either side, right? So concave down, over approximation, concave up, under approximation. So you can see this one's 2 points. You get the first points for evaluating the second derivative correctly. Again, you don't get any points if this is all you wrote. You need to show your work. And the second point is going to be if you find that it's concave up or down, and if it's an over approximation or under approximation. So you need to have the actual answer, it's an over approximation, and you need to have the reason. We have it as concave down, or the second derivative is less than 0. For part D, this one's fun. We want to use separation of variables to find an expression for m of t, the particular solution to the differential equation which they gave out with the initial condition. So what I did first was I just rewrote the equation, and what we're going to use is separation of variables. So what the first thing I'm going to do is multiply that dt over. So I get dm is equal to that whole thing times dt. Now I want to move all the m's to one side and I want to move all the t's to the other side. So what I do is I divide over that 40 minus m. It is okay that the right side doesn't have a t, that scalar can just hang out. But what we're going to do is now that we have all the variables on the same side, I'm going to integrate both sides. So on the left side, when we integrate, it's going to be natural log of 40 minus m, but actually it's going to be negative natural log, right? Because the derivative of 40 minus m is negative 1. So we need to make sure we include that extra scalar. And on the right side, that one's nice. That's just going to be 1/4 t plus c. So before I even continue simplifying, I'm going to go ahead and use our initial condition. We have that the point is 0, 5, so t 0, 5 is m, and we can just plug that straight into our equation. So we get negative natural log of 40 minus 5, and then that 1/4 t, we plug in 0, so that just goes away, is equal to c. So here we can find that c is equal to negative natural log of 35. So here I can go ahead and just plug that back into our equation. I replace c. So the first thing that I did was I multiplied that negative 1 over. So I get positive natural log of 40 minus m is equal to negative 1/4 t plus natural log of 35. And now what I'm going to do to get rid of the natural log, I'm going to have both sides. I'm going to make the base e and that the exponent, right? So notice what happens here. We have e to the negative 1/4 t plus natural log of 35. Well, we can go ahead and use exponent rules. That becomes e to the negative 1/4 t times e to the natural log of 35. When we have e to the natural log, those cancel each other out. So we're just left with e to the negative 1/4 t times 35, or you could bring that scalar to the front, which is what I did right here. We get 40 minus m because, again, these e's natural log cancel out, so we're left with 40 minus m is equal to 35 e to the negative 1/4 t. Now our last step is we're trying to get m all by itself. So what I do is, because the m's negative, I add it to the right side and then I subtract over the 35 portion. So I get 45 minus 35 e to the negative 1/4 t is equal to m. And that should probably be m of t because that's what they asked for. And that right there is our particular solution. So this one's actually worth 4 points, which is quite a bit. And we're going to see where that's dispersed out. So the first one is for doing correct separation of variables. The second one is for taking the correct antiderivative. The third point is for using the initial condition and finding the value of c. And then, this right here is all going to be the fourth point where you actually evaluate it, simplify it through correctly. So that's quite a bit of algebra in this one. I think separation of variables is fun, but that's my opinion. And that right there is our first problem. Let's try the second one. Well, the fourth one technically. We have the function f is defined on the closed interval -2 to 8, and it satisfies the point f of 2 equals 1. The graph, which is a derivative of f, consists of two line segments and a semicircle as shown in that beautiful figure. So part A, does f have a relative minimum, maximum, or neither at x equals 6? And we're going to give the reason for the answer. I'm going to scroll down here. I have it rewritten out. Let me zoom in. So notice at x equals 6, we're going to look on either side of 6 to see if it's a minimum, maximum, or neither. On the left side of 6, we have that our first derivative is positive. So the first derivative is greater than 0 on, and I just included 2 all the way up to 6, right? And we also have on the other side of it, the first derivative is still positive. So notice that the first derivative does not change signs. So since it does not change signs on either side of 6, that tells us neither a relative minimum nor relative maximum occurs at x equals 6. This one's only 1 point, and you get 1 point for saying it is neither with the reasoning. And the reasoning is that the first derivative does not change signs. So there you just get plus 1 point. Generally speaking, let's just talk about relative min and maximums real quick. A relative maximum occurs where our first derivative changes from positive to negative, right? It changes from increasing to decreasing. A relative minimum is going to occur where our function changes from decreasing to increasing, right? It's negative, then it's positive, it's first derivative. A neither is going to occur when it just doesn't change signs at all. So it could also have been negative and negative, but whatever. So that's the first part. Let's go ahead and go to the second part. On what open intervals, if any, is the graph concave down? So remember what derivatives are. The first derivative represents the rate of change of the function. So if the rate of change is negative, or the first derivative is negative, the function is decreasing. So now you got to think a step further. The second derivative represents the rate of change of the first derivative. So where the first derivative is decreasing, the second derivative is negative, aka the function is concave down. So we're looking for when the function is decreasing, the first derivative is decreasing. So if we look at our actual graph, we can see it's decreasing from -2 to 0, which I think is going to be right here. Oh, nope, I'm not going to reveal it yet. And we also have it's decreasing from 4 to 6. And those are the two intervals where it's going to be concave down. So this one's worth 2 points. Let's talk about where the points are. First, you have the explanation. So if you know that it's going to occur when it's decreasing, that's 1 point. And then you get 1 point for saying both those intervals. For part C, we're going to evaluate this limit or show that it does not exist. We need to justify our answer. So notice that we have our actual function inside the limit. And remember, in order to evaluate the limit, we want it to be continuous. So we can look at this graph and show that this function is differentiable, right? We have its derivative throughout the whole thing. Therefore, since it's differentiable, it is also going to be continuous, which I have written out right here. So since the function is differentiable at x equals 2, it's also going to be continuous at x equals 2. So let's go ahead and try to evaluate this limit. We're going to go ahead and look at the top first. We're going to go ahead and try to plug in 2. And remember, it gave us that f of 2 was equal to 1. So here we get 6 minus 6, which is equal to 0. So the numerator is going to approach 0. Now in the denominator, we can just go ahead and plug in 2. So we get 2 squared minus 5 times 2 plus 6. That's equal to 4 minus 10 plus 6, which also goes to 0. So notice here the numerator and the denominator approach 0 over 0, which is going to be indeterminate form. Since it's indeterminate form, we can go ahead and use L'Hopital's rule. So let's go ahead and evaluate that. We're going to take the derivative of the numerator. We get 6 times f prime x minus 3. The derivative of the denominator is going to be 2x minus 5. So now let's go ahead and plug in 2. We get 6 times f prime of 2 divided by 3, divided by 2 times 2 minus 5. So let's go ahead and find f prime of 2. F prime of 2 is going to give us a value of 0. So that's going to be super nice to plug in. We get 0 minus 3 is negative 3 divided by negative 1, which gives us positive 3. So this one is worth a total of 3 points. The first one is going to be finding that it approaches 0 over 0. The second point is going to be actually taking L'Hopital's rule, so taking the correct derivatives and stuff. And then the third point is just going to be you actually evaluated it correctly. If you gave just an answer of 3, you're not going to get any points. You need to show your work. Part D. So we have the find the absolute minimum value of f on the closed interval -2 to 8. Justify your answer. So Relative extrema is going to occur when the first derivative is equal to 0, right here and right here. So I have that written out. We have the values -1, 2, and 6. Let's talk this through first. Let's first talk about x equals -1. At x equals -1, the first derivative is changing from positive to negative, which tells us our function is changing from increasing to decreasing. Increasing, decreasing, that's going to be a relative maximum. So that means that f prime x changes from positive to negative, resulting in a relative maximum. So we can rule that one out. We don't need it. Now let's go ahead and talk about x equals 6. We already talked about this in the first part. So we have neither a minimum nor a maximum occurs, which is explained in part A. So that's my reasoning. We can rule that one out. Now don't forget, when we are testing for absolute extrema, we have to include the endpoints. So let me erase all this nonsense. So the first endpoint is going to be -2. The second endpoint is going to be 8. Notice what happens here. We do have a relative minimum actually occurs at 2, but our function after 2 is going to be positive the entire time, which tells us it's only going to be increasing. So let's talk about what that means. So on the interval 2 to 6 union 6 to 8, we have that the first derivative is positive, which tells us that f is increasing on that entire interval, meaning f of 8 is going to be bigger than f of 2. It's only increasing after that, therefore it has to be a bigger value, right? So the only two values we actually care about checking right now is going to be the left endpoint, f of -2, and it's going to be f of 2, which is our relative minimum. So they already told us the point, 1 comma 2, f of 2 is equal to 1. So now what we have to do is calculate f of -2, so let's go ahead and do that. Remember what we're trying to do is we're trying to find the area between the curve and the axis. So what we're going to do is we're going to go ahead and start at f of 2 right here, because we already know that value is equal to 1. And then we're going to add on the additional area. So first we have this big old triangle, which I'm actually just going to split into 2 triangles. So let's go ahead and find the area of this triangle first. We're going to the left 2, which is going to be an x value of -2. And then we're going down 2, so that's going to be -2. So the area of this triangle is going to be 1/2 -2 times -2, which is going to be a value of +2. So first we have 1 plus 2. Let's go ahead and find this other triangle right here. So here we're going to the left, which gives us a x value of -1. We're going down 2, which gives us a y value of -2. 1/2 times -1 times -2, that's going to give us a +1. So we have to do our last little triangle right here. That's going to be this area right here. We're going to the left -1. That's going to be your x value, but now we're going up 2. So that's going to be 1/2 -1 times 2, which actually is going to give us a value of -1. So finally, what we have is -1. So f of -2 is actually equal to 3. So comparing these 2 points, we have f of 2 is going to be smaller. So the absolute minimum occurs at 2, 1. So there are multiple ways you can do this problem. The reason that I decided not to just straight up test every value is because I didn't want to add up the area every single time. Because look at this semicircle. Do you want to try to add that area? No. So I used reasoning instead. Your reasoning gives you 1 point if you reason through it correctly. So 1 point is for that. You actually get a point for just showing the values, the critical points. That gives you a point. And then the last point is for actually finding the minimum value, the absolute minimum. Moving on to question 5, we have that the functions f and g are twice differentiable. The table shows these values in the first derivatives at selected x values. So for part A, I'm just going to scroll down here real quick. Let me zoom in. We have let h be a function defined by h of x is equal to f of g of x. So we have a composite function. We want to find h prime of 7, and we need to show our work. So the first thing I did was rewrote the function. And what we're doing is we're taking the derivative of it, which means we're going to have to use chain rule. So we do the derivative of the outside at the inside. So f prime at g of x. And we need to multiply by the derivative of the inside. So we multiply by g prime of x. Now we're trying to find h prime of 7, so we can replace, x is equal to 7 everywhere. And first what we need to do is find g of 7. So I'm going to look at my x's. I have 7. I'm going to go to g of 7, which is equal to 0. So first we have f prime of 0. We can also find g prime of 7. So g prime is going to be right here. So that's going to be a value of 8. So now that we did that, we need to find f prime of 0. So I'm going to go to my 0. I'm going to find f prime, which is going to be 3/2. So we get 3/2 times 8. We have that 8 divides by 2, so that's equal to 4. 3 times 4 is equal to 12. And that right there is our solution. Let's talk about the points. This is going to be 2 points. The first one is for doing chain rule correctly, so you need to show your work. The second one is just going to be evaluating it down correctly, so you plugged in the correct points. Let me zoom out so you can see all of that. So for part B, let k be a differential function such that k prime of x is equal to f of x quantity squared times g of x. Is the graph of k concave up or down at the point x equals 4? And give a reason for your answer. So when we're talking about concavity, that means we're talking about the second derivative. So here's our k prime. I already wrote it down. What we want to do is find its second derivative. So we're going to take the derivative of both sides. On the left, you just get the second derivative of k. And what we're going to have to use is product rule. So I have the first, which is just going to be the same thing, multiplied by the derivative of the second, g prime of x, plus now we're going to take the derivative of the first function, which is actually going to be chain rule. So we take the derivative of the outside. We do exponent rule. We bring the 2 down at the inside, so 2 times f prime of x. And we multiply by the derivative of the inside, which is f prime of x. And now we need to multiply by the second, which is just g of x. Now we're evaluating this at x is equal to 4, so we can just plug in 4 everywhere. And now we're going to go ahead and use our chart. So x is equal to 4. Let's go and find f of x first. F of 4 is equal to 4. So here we have 4 squared, and then on this other side we have 2 times 4. Now we need to go ahead and find g prime of 4. That's going to be right here. We get a value of 2, so we get g prime of 4. We need to find f prime of 4, so really we're just finding all of these values. That's going to be positive 3, and then g of 4 is going to be our remaining one, which is going to be negative 3, right? Now we get to do algebra. So first we get 4 squared times 2. That's going to be 16 times 2. I multiplied 2 times 4, which is equal to 8. 3 times negative 3 is negative 9. We get 32 minus 72, which gives us negative 40. So remember, we're talking about concavity. Since the second derivative is less than 0, it's negative. That tells us that k is concave down at x equals 4. We also have included, this was in the rubric, that k is continuous. You know k is continuous because it's differentiable. I don't know why it's necessary to say that. I know it's necessary for it to be continuous. I don't know why they want you to have it written, but better safe than sorry. So this one's 3 points. Where are those points awarded? Of course, it's going to be taking the second derivative correctly, so you get 1 point there. Another point is for evaluating it down correctly and getting negative 40. And the third point is interpreting that. So you have, since it's negative or less than 0, that it's concave down. And so that's going to be where your third point is. Part C, we have let m be a function defined by m of x equals 5x cubed plus the integral from 0 to x f prime of t dt. We're going to find m of 2, and we're going to show the work that leads to our answer. So what we want to do is plug in x is equal to 2. So that's easy for the first part. You just plug in 2, you get 5 times 2 cubed. For the second part, we're changing the bound of our integral. So we go from 0 to 2 of f prime of t dt. So right here, I just multiplied 2 cubed, which is equal to 8. So 5 times 8. Now the integral of f prime of t is going to give f of t, right? So we get f of t evaluated between 0 and 2. So multiplying this, we get 5 times 8 is equal to 40 plus, and now we do upper minus lower. So f of 2 minus f of 0. We can go ahead and look at our chart. We have f of 2 is equal to 7. F of 0 is equal to negative 10. So plugging that in, we get 40 plus 7 minus 10, which is equal to 37. And you can see my little plus 1 right there. You only get 1 point on this problem, and you have to show your work. So if you just wrote 37, you're not going to get any points. Showing all the work and getting the correct answer, that's going to give you 1 point. Okay, part D. Is the function m, which is defined in the previous part, increasing, decreasing, or neither at x equals 2? When we're talking about increasing or decreasing, that's going to clue you into the first derivative. So let's go ahead and find the first derivative of this function. So m prime of x equals, the first part's nice, so 5 times 3 times x to the power of 2. That's going to give us 15x squared. The second part is the fundamental theorem of calculus. When we differentiate this, the integrand stays the same, and you plug in the bound that has x. So we get f prime of x. If it was switched, if the bounds were switched, so let me show you this. If it was from x to 0 of f prime of t dt, what you would do is you'd rewrite that as negative 0 to x f prime of t dt. And when you take the derivative of this, right, taking the derivative of the original one, that's going to be negative f prime of x. So that's super important to remember. Otherwise, we're going to move on forward here. So what we're wanting to do now is we want to see if this is positive or negative. So let's go ahead and plug in 2. Plugging in 2, I just straight up plugged it in. So we get 15 times 2 squared. That's going to be 15 times 4. Looking at our chart, which is just going to be right up here, we want to find f prime at 2, which is going to be negative 8. So we get plus negative 8. 15 times 4 is going to be 60 minus 8, and here we get 52. So since the first derivative is greater, I forgot my C there. Since the first derivative is greater than 0, that tells us that the graph of m is going to be increasing at x equals 2. So where are the points awarded? The first one is taking the derivative correctly. The second one is evaluating m prime of 2 and finding the correct answer. And the third one is interpreting it. So we have, since the first derivative at 2 is positive, that the graph of m is increasing. That's going to be your third point. Okay, problem 6, we are on the last one. By now on the AP test, you're probably brain dead. So consider the curve given by 6xy is equal to 2 plus y cubed. Oh my gosh, it's everybody's favorite. We're going to do implicit differentiation. So what I did first was I want to take the derivative of both sides of our original function. So we want to show that this implicit differentiation dy divided by dx is equal to this. So what I did was I used product rule, and I'm going to show product rule in this one. So my first is 6x, our second is y. So the derivative of the first is 6 because we're taking the derivative in terms of x, but the derivative of g is going to be a little different. It's the derivative of y in terms of x. That's where we get our dy dx. So multiply 6 times y, we get 6y plus, and then I did the opposite. I multiplied these two together, and I got 6x times dy dx. So now we're going to go ahead and differentiate the right side. So the derivative of 2, that's just going to go to 0, right? Now the derivative of y cubed, we're going to take it like a normal derivative, 3y squared, but we have to multiply by the derivative of y in terms of x. It's like chain rule, and the inside is going to be y. So now what I want to do is I want to get all the dy dx's to the same side. So I'm going to subtract over that 6x dy dx. The purpose of doing this is so I can go ahead and factor out dy dx. And I have my leftovers 3y squared minus 6x. Since I factored it out, I can go ahead and just divide it over. Now, we're not quite done, right? Because we can still divide a 3 out of all these terms. So if I divide a 3 out of all of them, I get a 2, that goes away, and I get a 2 right there. And so that leaves us with 2y divided by y squared minus 2x. And that right there is our confirmed result. So we get 2 points here. The first one is taking the derivative correctly, and the second one is simplifying it down and actually showing what it equals. Okay, part B. Find the coordinates of a point on the curve when the tangent line of the curve is horizontal. So when is this going to occur? I'm going to draw a random something like that. That's a beautiful function. When is the tangent line going to be horizontal? Well, that's going to be where it's something like this, right? And that's where the first derivative is equal to 0. It has a 0 rate of change. So the tangent line is horizontal when the first derivative is equal to 0. So let's go ahead and set it equal to 0. The only time it's going to be 0 is when the numerator is equal to 0, and here we can solve that down and get y is equal to 0. So what I want to do is I want to take our original equation, 6xy is equal to 2 plus y squared, and I want to plug in y is equal to 0. So when I do that, I end up getting 0 is equal to 2. This is not a true statement, therefore there's no solution. So we have, since there are no solutions, no such point exists. This one is worth a total of 2 points. The first one is just finding that y is equal to 0. And of course, you need to show your work, not just write y is equal to 0. And also plugging it in and showing that there's no solution and explaining there's no point that can exist. So that's where you get your 2 points. For part C, we want to find the coordinates of a point on the curve where the tangent line of the curve is vertical and explain why no such point exists. Or explain. God. So let's talk about when a tangent line is vertical. So if we have a tangent line like this, let's think about the slope, because the slope represents the first derivative. The slope is going to be change in y over change in x. So right here, if I just take 2 random points, I go up 3, so the change in y is going to be 3, but I don't go over anything. I go over 0. So the slope is undefined. So we want to find where the first derivative is undefined. So the derivative is going to be undefined when the denominator is equal to 0. So I set the denominator equal to 0. I added over 2x. And right here, you can decide whether you want to solve for y or you want to solve for x. I always suggest solving for the variable where you don't have to take any square roots or anything weird like that. So I solved for x, I divided over that 2 so I don't have to deal with the square root. I think it saves time, but it's personal preference. So plugging this into our original equation, we're going to plug in x is equal to y squared divided by 2, right? I replaced my x right here. We're going to go ahead and solve that through. So first we have that 6 divided by 2 is equal to 3. So we get 3y squared times y is equal to y cubed is equal to 2 plus y cubed. I'm going to subtract over that y cubed, and then I'm going to divide by 2. Taking the cube root of both sides, we get y is equal to 1. So we can plug that back into x. Y is equal to 1. We get 1 squared divided by 2, which is equal to 1/2. So here we have the tangent line is vertical at the point 1/2 comma 1. So this one is worth 3 points. The first one is right here where you set the denominator equal to 0 and you solve for one of the variables. You can do either of them, so either way was totally correct. The second point is finding what the y value is equal to. And then the third point is plugging it in, finding the x value, and saying where the tangent line is vertical. So you have to say it as a point. Make sure you do x comma y. It's easy to switch them off when you're, in AP test mode. But that's where you get your 3 points. Okay, finally, you're on your last problem. You're not crying yet, which is great, right? We have a particle is moving along a curve. At the instant when the particle is at the point 1/2 negative 2, its horizontal position is increasing at a rate of dx over dt is equal to 2/3 unit per second. What is the value of dy dt, the rate of change of the particle's vertical position at that instant? So remember the equation that we're working with. We're working with 6xy is equal to 2 plus y cubed. Now what we're doing is we're taking the derivative in terms of t, not x anymore. So I'm going to take the derivative of both sides in terms of t. So again, I'm going to show product rule. We have our first one is 6x, our second one is y. So the derivative of 6x is going to be 6 times the derivative of x in terms of t, right? Our second one is going to be the derivative of y in terms of t, and that should be g prime, right? Because we're taking the derivative. So here what we do is I'm going to cross multiply. So I cross multiply these two together first. We get 6y times dx dt. Now we can cross multiply again, and we add those together. So we get plus 6x times dy dt. Now on the right-hand side, the derivative of 2 is still going to be 0. So we get 0. And now we're going to take the derivative of y cubed. So we get plus 3y squared times dy dt. Now we actually have a ton of information we can plug in right here. The first piece of information is that we already know what our y value is equal to. The y is going to be negative 2. So we have 6 times negative 2. They also gave us dx dt. Dx dt is 2/3. So we get times 2. That should be a 3. And then we get plus 6, and now we can multiply by x. And they gave us what our x is equal to, and that's going to be 1/2. So we get 6 times 1/2 times dy dt, and that's what we're actually looking for, so that's going to just stay dy dt, is equal to, so we have that 3, we have our y squared, that's going to be negative 2 squared times dy dt. So here we can simplify this down. Right here, the 6 divides by 3 to be 2, so 2 times negative 2 times 2, that's going to be negative 8. We got 6 times 1/2 is equal to 3 dy dt. 3 times negative 2 squared, that's going to be 3 times 4, which is equal to 12 times dy dt. Now we're going to follow the same process. What we want to do is get the dy dt's all to the same side. So I'm going to subtract over 3 dy dt. So we get negative 8 is equal to 9 dy dt. We can divide by that 9 over, and we get our solution. So this one is worth 2 points. We get our first point from taking the first derivative correctly, so the derivative in terms of t. The second point is going to be evaluating it down all the way to negative 8 divided by 9. If you just wrote out negative 8 divided by 9, you are going to receive no points. So make sure that you show your work. And on FIN, or just FIN, we have the end of the exam right here. So that is all I have for us today. If you enjoyed this video, I have many more like it. So make sure to check out my playlist. They're linked down below. Please let me know if you enjoyed this version. I feel like I get to talk and explain more, but if you guys like if I write more, just let me know. But please leave this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.